Thank you, everyone, for coming. There are plenty of seats left, so you can come back from the back. So today we're going to talk about generators and coroutines, and I'm really only going to give you a taste. And we're going to look at coroutines from the user point of view and not really explaining a lot of the compiler magic that goes on behind the scenes. So I hope this will stimulate you to go and learn more about the subject and also give you some motivation about when and how coroutines are used. So let's talk about functions. Say we want to write a function to iterate over some sequence. Now, this function actually does two things. It iterates over the elements of the sequence, and then for every iteration, it applies some kind of operation. Now, what if we need to do some other operation? Maybe instead of summing the values, we want to print them, or both sum and print. So in each case, we actually have to write a new function. Now, let's look at another example. Let's say we want to draw a line. So in this case, this is a typical algorithm you might see in online articles or books about graphics, how to draw, to rasterize a line. This is a partial Bresenham in this case. And what you can see, it's a very typical algorithm where we're iterating over the sequence. In this case, this is the pixel positions along the line. And then we're applying some kind of operation at each of these pixels. In this case, it's drawing the pixel to the screen using the function putPixel. Now, notice that this function actually makes several assumptions about this external function, which is called putPixel. It assumes that it's actually available. So the code needs to compile and link. It assumes that the signature, of course, is correct, and that the function actually does what it expects it to do. Because we're actually assuming, and this is kind of an implicit assumption that we don't tend to think about, but it's assuming that this function, this external function, will actually return control to drawLine in mid-computation. So we're actually hoping that we'll get back into drawLine so that we continue the operation. So we can see that functions, which are also known as subroutines, they have two properties. They're both eager and closed. So eager means that they're eagerly processing the whole sequence before finishing, before returning, and closed in the sense that they apply some predefined operation on each of the elements of the sequence, of the whole sequence. So one common mitigation of these two properties is to use callbacks. Many of us have seen callbacks, and in fact, C++ offers many, many different mechanisms for using callbacks. In the general sense, we have function pointers, we have lambdas, we have template parameters. Concepts also allow us to do similar things, and this is how a lot of the STL algorithms actually work. Now, callbacks themselves have their own set of problematic issues when they're overused. For example, inversion of control means that we're calling external code that's not necessarily trustworthy. We don't know if it's valid. We don't know if it's correct. And everything is done in mid-computation. So we have some kind of state inside of our own internal function. And we're kind of trusting the external code to do the right thing. Now, a second problem with callbacks, what's typically called callback hell, is the fact that the program control flow is skipping between many different decoupled parts of the code, and your code actually becomes very difficult to understand. It's difficult to reason about. If you need to maintain it or debug it, then we have to start jumping around between different parts of the code. Not to mention things like a lot of function calls can have performance issues, potential performance issues. So although when using callbacks we're not closed, the function using callback is still eager. It still tries to call the callback for every element of the sequence. So in this case, callbacks are not necessarily a full solution to the problem of both eagerness and closed function. So the question arises is whether we can break these functions open. If there only was a way to somehow flip these iterating functions inside out so that we can iterate over a sequence without committing to some predefined operation. And the answer is not a big surprise. We're all familiar with iterators. They're very common in the standard library, and they're typically standalone types. And if you'll notice, very often they're only indirectly or implicitly coupled to an actual sequence. The concept of iterators was introduced by Alexander Stepanov back in 1993. It became part of the standard library in 1998. And we have many, many, many examples in the standard library, and I'll just give 3 examples here. STD iStream iterator allows us to read elements from the stream using the input stream operator. We have STD reverse iterator, which is actually called an iterator adapter that reverses the direction of a given iterator. And in C++17, we got STD recursive directory iterator, which allows us to recursively iterate over all the elements of a directory and all of its subfolders. Now, the nice thing about recursive directory iterator, it shows us that the file system directory subtree is actually the hierarchy and the elements of the sequence. There is no concrete object in memory that we're iterating over. So it's only some kind of logical structure that exists outside the scope of our program, which we're iterating on. And this shows us this very loose coupling between iterators and the actual underlying sequence. Now, of course, we can also write our own iterator classes, and let's pick on OpenCV. OpenCV, it's the open source computer vision library. I've been using it for many years, and there is an interesting example there. It's a class called CV line iterator. Now, this is used to iterate over all the pixels of a rasterized line connecting 2 points. This is a quote from the documentation, and it has a very typical iterator API. There is no explicit sequence or underlying sequence. The iterator class, line iterator, basically computes the next pixel position every time the increment operator is called. So in this sense, it is lazy. There is no underlying sequence. The underlying sequence is computed lazily. And we can get incremental access to the pixels along the line. Now, you can see the API here. I basically copy and pasted. There's a lot of things we can say about this type of class design. And how do we use it? Well, it's actually very simple. We're looping, we're creating the line iterator, giving it 2 points, the beginning and the end. In this example, again, this is an example from the documentation. We're creating a vector which will hold the values of the pixels along the line. And then we're using a for loop to iterate over all the values. And you can see that the for loop runs from, it has some kind of integer index I, and it basically we're iterating until it.count. That count is the member that gives us the number of required iterations. And we're just copying the value of the pixel into the vector. The nice thing about iterator classes is that maybe we don't want to copy the values into a vector. Maybe we want to draw the line and onto some external image or external device and set some kind of colors, maybe make it a very colorful line. In this case, we can still do that, and the iterator class itself doesn't need to know anything about how we're planning on using these pixel positions or the values of the pixels within the line. And really, the possibilities are endless, and this is what I call the flipping the functions inside out, allowing us to iterate over the sequence. And whoever here has used iterators, which I guess is most of you, are familiar with the concept, because this is really the power of iterators. However, iterators themselves are an imperfect abstraction. They have several problems, which I want to talk about, which are not directly related to the actual implementation of line iterators. So I'm not going to talk about the public members or the pixel type casting that we needed. I want to talk about the more general problems that are inherent when we're trying to write iterator classes. And I call these the awkward coupling problem and the distributed logic problem. And let's dig into them and see what I mean. So the awkward coupling problem is basically what happens when we ask, when do we stop incrementing our iterator? Because every iterator class must know how to answer this question. And if we look at only the 4 examples we've seen until now, CV line iterator we just saw has the it.count member, which tells us how many times we need to iterate. The standard iStream iterator class compares equal to some kind of global default constructed iStream iterator object. So this is another type of policy to decide. The reverse iterator adapter becomes equally comparable to the our end iterator returned by the underlying sequence, and recursive director iterator becomes equality comparable to calling the global std end function over the iterator itself. So we're actually seeing 4 different ways of answering the same question, and of course many other examples might give us other ways of answering this question, and this causes a problem in the abstraction of iterators. And even worse is that if we look at the last 2 examples of reverse iterator and recursive director iterator, if we're trying to pass 2 begin and end iterators to some kind of STL algorithm that requires a begin and end, we're actually depending on the user to pass the correct begin and end of the same underlying sequence. Let's say we have 2 director iterators, or 2 reverse iterators, and we actually accidentally switched between them, so we're passing the begin of one iterator and the end of another underlying sequence, then this is undefined behavior. There will be the same type, everything will compile successfully, but we're actually going to have undefined behavior, and because we're breaking the terms of the API. So this is a kind of a responsibility put on the class users, which we want to avoid. And of course, one of the solutions, or a major solution to this problem of the awkward coupling is ranges. In C++20, we're getting ranges. I'm not going to talk about the huge power and enormous power that ranges bring with them to C++20. But essentially, they're an abstraction layer on top of iterators. And they allow us to encapsulate a begin iterator and an end iterator, or maybe a begin iterator and a size, or an iterator and some kind of stopping condition into a single object, which we can manipulate as a single object. And it allows us to allows a lot of the STL algorithms to become composable, and we could create pipelines, and there are many excellent talks and papers that show how to use ranges. However, since ranges are essentially an abstraction over iterators, when we come to implement ranges, they are still at heart suffer from the second problem that I will mention about iterator classes, and that's the problem of distributed logic. So if we look at the same implementation, at the files for CV line iterator, we can see distributed logic is really it's the cousin of callback hell, because the implementation itself has the properties where the logic of how the iterator works is actually distributed among different methods. For example, in CV line iterator, this is I kind of narrowed down the example, but you don't see the implementation of the constructor, but a lot of the initialization goes into the constructor, and then the user is going to write some kind of loop and call the increment operator and the dereference operator, and then in these methods, we're going to have additional logic. So while the loop iteration is externalized, a lot of the intermediate computation is split between different methods. So when we're trying to write this code, when we're trying to read this code, when we're trying to maintain it, when we're trying to debug it, we often have to jump between multiple methods, and some iterator classes may have more than one increment. Maybe there's a post increment, maybe there are other operators that we can think of in different circumstances. And that gives a very large mental load for whoever is writing these classes. And in addition, we have the opposite problem where since we have to stop in mid-computation to give a value, an intermediate value, all of the state variables are stored as mutable members. So instead of saving them as local variables within some kind of loop, like we saw in the first example, now they're all members, and all of our methods can access them. So we're basically giving up a lot of the scoping rules that C++ gives us, a lot of the protection of local variables, and everything becomes sort of global to the class implementation. So if we look at this implementation of CV line iterator, we can do kind of a copy-paste thing where we can use the open, the lazy and open iterator class on the right, but which suffers from the distributed logic problem, and then sort of just copy all of the internal implementation into a single function, which I call process line in this example, But now everything is localized. So we have centralized logic. However, it's eager and closed. In this case, it's doing something, right? There's the function do something, which is going to do something to the pixel. This is the operation that we're committing to by the fact that we're using a subroutine. So we kind of have this trade-off between lazy and open or eager and closed, and the price we're paying is the price of implementation logic and implementation where the data is stored. So now we're going to the next question is, can we have nice things? You know, it's, if only there was some way to write an easy to reason about serial looking code like the function on the left that we saw, like a process line here, that is still allows us to abstract away the iteration, somehow allow us to do these, not commit to some predefined operation when we're writing our class. And this is what coroutines are really one of the essential properties of coroutines. This is what they allow us. Now, just to make sure, coroutines are not a new concept. They've been around since 1958. I think most of us, or if not all of us, were not even born by then. And Boost has had several implementations of coroutines for at least the early 2000s, and I've seen C implementations as well. So it's not a new idea. But you might ask, okay, what is this coroutine? So a coroutine, in essence, is a function that can suspend execution. It can stop in mid-computation, return some kind of intermediate value, and then, upon request, resume later from the same point where the reentry happened. So it's sort of a kind of a pause button that can be pushed or can be chosen by the programmer and then resume from the same point. And this is in contrast to threads, which are preemptive. So threads are usually interrupted by the operating system. In coroutines, the switches are called cooperative. So the programmer actually controls when the switch happens. And there is no kernel scheduling involved with coroutines. So coroutines are only, in this context, they're a totally user-side programmer decision. Now, if you think about it for a minute, we just saw process line, which is a very nice serial logic, but then it does something, and essentially this is what we want. If this process line example was a coroutine, instead of calling do something in the loop body, we could just suspend execution and yield this value to be used by the external user, and then the user may resume the computation wherever it left off. And now, this is exactly what we wanted, and happily for us, C++20 is probably getting coroutines. They were also approved, but into C++20, and hopefully we'll be seeing a lot of them soon. And they are, as I explained, the answer to distributed logic, and I'll show you why in a minute. So a C++20 function is a coroutine if the body of the function uses one of the three keywords. So if it uses the co-await operator to suspend execution until it's resumed, if it uses the co-yield keyword or co-return keyword to complete execution. Now, how do we know if a function is a coroutine? How do we know if a function is a coroutine? We can't. So not from a signature. So the header file that of maybe the prototype, the initial, the forward declaration of a function, we can't actually know if a function is a coroutine, because coroutines, and this is a really, really important aspect, are an implementation detail. They're not something that the user of the function needs to know how the function was implemented. So hypothetically, you could implement something that looks like a coroutine and has a return value of a coroutine, but it isn't actually a coroutine. And we'll see a very simple example of that in a minute. So it's important to understand that coroutines are an implementation detail or implementation aspect where the compiler is actually going to do some nice compiler magic for us, or it's kind of syntactic sugar on steroids. Now, there's a lot to talk about C++ coroutines, and it's a huge subject. And I'm actually going to talk only on a very narrow view of creating what's called synchronous generators from the user perspective. So I'm only going to focus on the co-yield keyword and the co-yield, sorry, the co-weight and co-return, we'll have to wait to another talk. But I still think this is a really nice view of what things looks like. So let's look at some code. So we have a little function here. It's called Zorro. What does it return? It says up on the slides, it returned 42. And the return type is int. Is it a coroutine? No, why? Because it doesn't implement, we can see the implementation, it doesn't contain any of the three keywords, co-yield, co-return, and co-weight. Okay, so now let's look at this little function. It's called coro. It co-yields 42. What does coro return? It doesn't return an int. And what is the return type? It's not int. Is it a coroutine? Yes, it is a coroutine. Okay, so we can see that the code actually looks very, very similar. So let's see how we can use coro. And basically we use it like we use any other iterator object. So a generator is a range, so we can just put it in a range for loop, which in this case, of course, will run just once. So we can see in the top example, we're just putting in a range for loop. We print out the value. In this case, the loop will run once. It will print 42 and finish. We can also break it down and use it like we would use any other iterator class. We can call the coro, get the generator object, then call begin, access deref begin, and then or even do it in a single line, which is much more verbose. So obviously, single element ranges are not very interesting. They're actually rather boring. But however, since coroutines are lazy, we can easily generate infinite ranges. So in this example, the infinite loop will suspend at every iteration and yield the current value and only resume on demand. So we have this function iota. It takes some kind of it takes a value n, and then it just returns n incremented by 1 until it reaches, well, it won't reach infinity. It will wrap. But we can see this program will actually only, then we can use copy n. We have iota of 42, and we can print the first 9 values. Since the range is lazy, we don't have a problem. There is no infinite loop in this program. So this is all really nice and very pretty. But I actually lied to you. So although all of this code which I showed you it does compile and it does work, it's actually not standard conforming, because coroutines are not at this time allowed to have an auto return type. And if you remember all the examples I showed you had the auto return type, and that's in fact only a Microsoft Visual Studio extension. When it sees the auto return type, it infers it to be an instance of a class called std experimental generator, and it puts the type of the core-yielded value into this generator. Now, maybe the auto-return type will be supported in the future. However, in C++20, it cannot be supported. And this is the sad part, is because there is no such standard class as std generator. And why is that? That's because the C++ standard for C++20 will not ship with any standard coroutine support library. So the coroutine facilities inside of C++20 are actually very, very low-level instructions of how the compiler transforms code and how it interacts and collaborates with library types which adhere to certain APIs, but those library types at the moment will not be provided by the standard library. So in this case, in the examples that I'll show here, I'll be using Microsoft's experimental implementation. And hopefully, I know that for C++23, having a coroutine support library is one of the highest priorities. And by that time, I hope we will have it as part of the library. Until then, you can use Louis Baker's. There's a fabulous CPP Coro library that's very, very suitable and can run on all of the compilers that actually, if you're not using Microsoft's own implementation, you can use that on other compilers as well. So now let's see some more interesting examples. So I do a lot of image processing and computer vision, and I once needed to process the neighborhood about around some pixel in the image until I find the closest neighbor. And for various reasons, my solution was to scan the image in an ever-growing spiral until I bump into the first neighbor. Now, the way it turned out that this is really, really nice way to write that spiral or spiral generator is something that's it's very elegant to write. And the code, you can see the code on the left, and you can see this code, basically it spirals, first of all, it's image independent. It starts at the coordinate 0, 0, and then starts spiraling around it into infinity. I'm actually not going to explain how it works, but I do want to point out that when you want to reason about this code, it's much easier to do it when the logic is centralized in a single serial function, like you can see here, than if it was split between different methods of some larger class. So in this case, we have a loop, and the loop co-yields the current pixel position or current coordinates of the pixels. Now, if we want to actually draw this spiral with the pretty colors like we see in the animation, then we need to generate some colors, and in this case, we need to create RGB colors, which are the ones that our screen can display. And to get all the nice, highly saturated color, we're going to use the HSV color space. So in this case, I'm using OpenCV. I'm creating a 1 pixel image, and I'm basically iterating on the hue value of the channel, and using OpenCV to convert at every iteration. I'm converting from HSV to RGB, and co-yielding, you can see the second to last line, I'm co-yielding the RGB color for the current pixel. Right, so to draw the animation, all that's left to do is really create a generator. We need to create 2 generators, one of the spiral and one from the hue cycling, and then lazily iterate over them in tandem, in lockstep, to generate the animation. So we would like to use a range for loop to iterate over these 2 generators, but the question is, how do we use a 1 range for loop to iterate in tandem over 2 generators? And the answer, of course, is let's zip them together. So we can see on the top, we can see the zip function. This is a very, very simple zip function. And if you see, coroutines can be templates as well. So we have this generic zip function. It takes 2 types. In this case, it assumes there are generators. It takes the begin iterator of each of these generators, and then it loops over them, co-yielding a pair of the current position and the current color. And every time it increments both of the generators to get the next value whenever we call the increment iterator. So now all we need to do is compose them together in some kind of range for loop. We can use C++17 structured bindings. You can see in the second example, it says auto, pose, and color. And pose, of course, will be the position. Color will be the color we want to paint. We can use OpenCV very easily and draw the images that we see here. And this is, in fact, the program that generated these animations. So let's see another interesting example. And say we have some kind of binary tree, and we'd like to iterate over its node. So we might write something like this code here. We have 3 class methods. So we can see now coroutines can actually be methods as well. One is called in-order, one is called pre-order, and one is called post-order. This is the regular tree ordering that we learn in data structure courses. And each one of them is, in fact, a different coroutine. And then there's another regular function. It's a non-coroutine called order that returns one of the coroutine generators. So I said you could have a function that's not a coroutine itself, that does have a signature or it does return a type that's typically returned by a coroutine. So this is an example of, so the method order is, in fact, a very simple example of that. So we can see here that each traversal function recursively traverses each child node, and then it key yields all of the values from the generator of the returned by the recursion. Then for example, if we look at in order, it starts on the left node. It recurses into left in order, co-yields all of the values generated by this generator, then it co-yields itself, and then it does the same thing to the right. And pre-order does the same thing, only in a different order, and of course post-order does the same thing in the third order. So this is really cool. And there are two interesting things that we can see here. First of all, you can note that order returns, it has an auto return type, and it's returning, it uses a switch case to decide which generator returned by one of the three methods to return. So because we know all of these would be STD experimental generator of ints. So in fact, it's returning the same type but three potential values. But you can see that each of these generators is generated by a different method. So in this case, and this is kind of a side note, there is some kind of, we can infer that there's some kind of type erasure going on in the background, because there are three different implementations all returning the same value. So if these were lambdas, we would not be able to return a single type of the three lambdas. So this is just a side note. But the second interesting thing is that you can see that all of these methods, most of the code, we're just co-yielding the values of another generator. So there's a very simple loop which just co-yields the value. And this is very tedious and very repetitive. So in the CPP Coro library, there's a really convenient type called recursive generator of T. And that's designed, in addition to the fact that it can co-yield the actual values that we want to yield, it can also co-yield itself, because co-yield is an operator. So we can overload the operator for different types. And in this case, I think we get probably one of the most succinct and clear implementations of, in this case, an in-order function, which basically we're checking if we have a left child, then just co-yield all of the values of the generator, basically co-yield the generator itself, and that will, externally, the user will be oblivious of the fact that we didn't have to write the extra boilerplate code. So I think this is super elegant, and I really can't think of any traversal function that can be more elegant and simpler than this implementation. So I think this is really cool. Now, you know, coroutines, we don't even have C++20 yet, and coroutines are not perfect. So we have to be careful when we're trying to play with coroutines and consider some of the pitfalls. And I think one of the most notorious pitfalls, and it pops up much more frequently than you might imagine in regular code, is called dangling references. Basically, in coroutines, the execution starts after the call, only after we're calling begin. So when upon the constructor of the generator class itself, the coroutine is called in an initially suspended state, and no function, the coroutine itself hasn't started executing yet. Now, if we look at this seemingly innocuous example, we have a simple for loop, and we have a coroutine called the explode, which takes a std string by const reference. And inside it iterates over the characters of the string and co-yields them one by one. And since it co-yields, it's a coroutine, and it returns the type generator of car. And it's called explode. And the way we use it is we have a simple range for loop where we're basically taking all of the values of the generator by calling explode with hello world and trying to print them out. Now this code actually does explode because we are passing a character literal to explode. Now that generates a temporary value, a temporary std string, which is taken by reference. In this case, it's a const reference. However, if we look at the range 4 documentation, it said that beware that the lifetime of any temporary within the range expression is not extended. So although we do have temporary lifetime extension of the objects when we're creating the generator itself, so the generator which is created by explode is getting lifetime extension, the string that's passed to it does not. So by the time that we begin executing the coroutine, that string is already long gone. So this is a very subtle point, a very subtle case. I'm kind of optimistic that compilers will be able to identify these cases. I know the previous studio folks are somewhere around here. And I think there is some work trying to mitigate these problems, but beware. And this is what I showed here is really the simplest problem, the simplest example of this. But when you start playing with coroutines, you might bump into it in more cases. Especially if we take, I saw an example where if you have a lambda and we capture by value, or we pass an argument by value, we're getting two different examples. So if we pass by value, as we saw here, it should work fine. There won't be a dangling reference. However, if we capturing the same value by with the lambda captures, then we will get dangling references because lambda captures become members and they don't get lifetime extension. So just beware and basically always pass your value. I think the main rule of thumb is always pass your temporary objects by value and not, pass the arguments by value and not by reference. Right. So as I said, coroutines are not perfect yet, and they do have several limitations. So although we saw examples of templated coroutines, we saw examples of they can be lambdas, and we saw that although I did use auto, they actually cannot use auto-deduced types. And the reason is because we don't have a standard library. Now they can also, at the moment, they can't use the regular return. So we have to decide whether we're using return or coroutine. I'm not sure this is going to stay, and I'm not even sure why it happens that way. And also const expr functions, constructors, destructors, and main cannot be coroutines. I'm not sure what it would mean for main to be coroutine, but it's defined as that way. And I think the main problem at the moment with adopting C++ coroutines is the fact that we don't have the coroutine support library, and I'm very, very happy that this is one of the highest priorities for the committee for C++ 23. Of course, there are problems of the fact that because there is no standard library, there is no standard library definition either. So Microsoft's implementation of the so-called STD experimental generator has a slightly different API than some other library like CPP Core. So maybe Microsoft does support taking a value by, or CPP Core supports taking a value by a reference type where Microsoft does not. So there are subtle differences which we must take into account. And the last problem is compiler issues. There have been several talks in CPPCon about how the compiler may elide a lot of the memory allocations that happen, especially in the case of generators. Synchronous generators are actually much potentially optimizable. So the code will be just as efficient as if we've written everything locally. However, again, there are compiler implementation differences, and I do believe that most of these things will go away and we'll see the performance improving. I did collect some resources for you. There's a massive, really a really massive list of coroutine related resources from the papers and discussions, the videos and everything related. On GitHub, you can see that link, and of course you'll have the slides online. CPP reference has a very interesting, a very detailed coroutine page. There's a coroutines channel on the C++ Slack, so if you're not on there, you should go there, and everyone who's involved with the standardization and using of coroutines, even for much more diverse applications like asynchronous programming, that kind of thing. Everyone, I think almost everyone is there. So and accessible, and you're welcome to ask questions there. Another link that I added just this afternoon is that from the last mailing, the pre-Belfast mailing, there is a national Bulgarian national body comment about postponing coroutines to C++23. So they have, it's a very quite a long list of reasons why they think it should be postponed. I don't know if that's going to happen. I may have to change my talk. But they have some interesting points there, and it's interesting to go and read. Most of this talk and a lot of extra details will be available on my blog. Yeah, so go ahead and play with coroutines, and they're really fun, and they make some code extremely easy to read and reason about, and they're fun to play with. But you know, like any C++ advice, you know, beware. So thank you. And now I'm happy to take questions.
Okay, if we have any questions, raise your hand, please. Okay.
Thank you for the talk. I have a couple of questions. First one is ranges library is written, I guess, for C++17 standard, and that's why it doesn't use coroutines, as I am concerned. So there is an option to move it to implement it with coroutines, and that will somehow ease the implementation of it. Do you know if it's considered in committee?
I think the C++ ranges, C++20 ranges are in fact C++20 specific, because although there is a C++17 implementation, the C++20 version uses concepts very heavily. So it does rely on concepts. So once you have a conforming compiler, that's only C++20. So whether or not they're using coroutines, I think that's an implementation question. Hypothetically, you could implement some of the ranges library. I think Eric Nibler is around here somewhere. You may go and ask him. I just showed you in 5 lines how to implement a very, very rudimentary zip. And in fact, I think C++20 will not have zip in the ranges library. But the range v3 library does have a much more generic implementation of zip, which doesn't use coroutines. As I said, coroutines should be thought of as an implementation detail. So as a user, you should be oblivious to whether or not it's implemented with coroutines or not. They will interact naturally with ranges not written using coroutines, because they are iterator objects.
Okay, thank you. And I forgot the second question. I guess I'll stop. Yeah, thanks.
Any more questions? No?
Have you measured performance decrease for coroutines?
No, I haven't. As I said, there are significant quality of implementation issues. It's still considered experimental until we get it ratified into the standard and the compilers declare that they're officially supported. Then doing performance testing is not necessarily something that's relevant.
Okay,
I saw some questions over there.
Well, thank you for the talk, but my question is actually very similar to the previous one, namely, what is the overhead for example, core yield is going to be? Will it be like for regular return or something else?
I'll repeat the question because I'm not sure I understood. You're asking if core yield is similar to a regular jump?
The question is about the overhead in coroutines. What if I use core yield? Does it cost the same as regular return operator, or it is more expensive?
Well, I did say, the first thing I said, I'm not going to talk about compiler magic, but I will try to answer your question. At the simplest level, the way the compilers interact with the coroutine support library is they break up your code and generate something. It's kind of conceptually similar to how a lambda is generated. However, there is some type erasure going on there, and this is where some of the cost will go, the extra cost, because there's memory allocation. But it does break your code up into small segments and then uses something like a switch statement to remember where it was before, depending on the number of co-yields you have. So the co-yield itself will be just a jump inside the switch statement. It will be just as efficient as that. The type erasure, if it's not elided by the compiler, will have some extra overhead. Whether it's worth it or not, I think it really depends on the complexity of the function you're trying to implement. So, like many other things, sometimes the cost is worth it. The more complex your code, your algorithmic code is, the more co-yields you have, and the wider interface you're trying to expose. Sometimes you may have very different code paths within the coroutine, which would make it extremely difficult to implement in a different way and still give the open API. So I guess it depends, which is the regular answer. Any other questions? Oh, yes.
Thanks a lot for the talk. The example with zip implementation looks really gorgeous to me. I mean, I've seen the implementation of zip iterator in Boost. Wow, that's a mess. Well, 2 questions. The first, probably simple. What's the difference between return and CO return?
At the moment, the C++20 does not allow coroutine to use return at all. So you can only co-return for a coroutine. And if you have one of the other keywords, you cannot use return. So you only have to use co-return. Now, co-return itself is really, it allows us to complete, return a value. And it allows the coroutine to return a value. Basically, it's like a co-yield, and then calling the termination sequence that happens. Basically, it calls all the destructors and just finishes the function.
Does it make any sense to use in a coroutine to use only co-return without await and yield, which essentially turns the function into a coroutine into a subroutine?
I think maybe for very trivial functions like the one I showed, the first one. This one. So maybe you could co-return.
Yeah, so what's the point? Is there any point in doing this?
This is a trivial example, so I don't know.
So unclear, right? Okay, and another question. So C++20 is not complete yet, right?
True.
Is there any chance we get rid of this ugly CO underscore?
Not in C++20. The answer is not in C++20. There is a paper that's trying to add some kind of, I forget the technical term, but basically allow you to write, let's say in this example, I have the iota and then add something like a new location-specific keyword like async there, and then in the functions that are decorated, it's a function decorator, then inside those functions, since nobody has ever written a function that contains that, then you may be able to drop the CO underscore. But again, this is a proposal. I don't know what its status is. But the simple answer is no, not at the moment. We're stuck with the CO underscore.
But what was the reason in introducing this? I mean, it's just the syntax, yield, space, something, semicolon. It cannot compile before C++20, so it cannot break any code, right? So why is it even used here?
I think it's somebody. I think they did some statistics over large code bases, and they found that the yield is used as an identifier name and as a symbol, and maybe as a macro in too many places, and it would break some amount of code. Although on the other hand, I would argue that maybe module would do the same, and it's not called co-module. So, you know, c'est la vie.
As I know, yield was widely used in financial software. I don't know details.
No.
Who was talking?
Thank you for the presentation. I have some kind of fun question. What do you think what would happen if we combine co-yield and recursion?
I just show you an example of recursion in the tree. This is, you can see, right,
sorry,
you see my mouse?
Missed it.
Here. You see, we're calling in order on the left child, and then we're calling in order on the right child. So there's technically no problem. A coroutine is a regular function, and it's treated like a regular function.
It's like it would generate a state every one you go deep in recursion, yes? It's like this?
It will generate a state on the stack, and if some more allocation happens within the construction of the generator, yes, that's how recursion works.
Oh, okay.
And in fact, I mentioned the CPP, the recursive generator here. I think that's one of the reasons it's not called generator. It has a special type because it's more efficient. In these cases, it will probably not, it will try to recycle some of these extra state that's generated.
No.
But again, I'm not sure exactly about the implementation details.
Thank you.
Hi, I have one more question. Possibly I have missed the point. Are there any limitation for using exception at the coroutines?
Well, all of the coroutines that I've shown here are synchronous. So they're basically code running within your thread, and it's just like running any other function. So exceptions will percolate just as they do in a regular code. Of course, if you have a co-yield and you're throwing an exception, well, if you co-yielded the value, then let me put it this way. If you're throwing an exception, you're not going to catch it inside your function if the catch statement is after a co-yield. Or maybe you will. No, it's just like any other regular code. It's synchronous code, and you're going to catch it like any other normal code. If co-yield happened, then it means it wasn't on the exception path, so you just co-yielded it. Maybe there are some things that can happen while you're co-yielding the value, but that's a little bit beyond the scope of what we're talking here.
Okay, so seems no limitation for exception.
No, not that I know of at the moment.
Thank you.
Any other questions? All right. Oh, maybe one last question over there. Oh, okay, two more.
Hello, thanks for the talk. The last time I checked, there was the proposal for coroutines actually included quite a lot of standard library facilities, but then there was this Google, I think, proposal called coroutines core. So does what you say mean that proposal was accepted and they basically removed all the standard library features after that? Or what exactly happened?
I don't know the exact story of the fine details and the differences between coroutine core and the full coroutine and the initial coroutine proposal. The last proposal, I think, did merge some of the aspects from both proposals, but it didn't. But the coroutine support library didn't make it into the C++20.
Okay, thank you.
And one last question over there.
Maybe not the last.
Okay, maybe not last. We have stuff.
Thank you for your talk. Well, that's right. Not the last. I have two questions. So the first one is, as I understood, it is possible to have a virtual function which would be overloaded and make that function as a coroutine, right?
A virtual function?
Yeah, the method, virtual method, which could it be coroutine?
Yeah, I think a virtual function could be a coroutine because it depends really on the return type.
Yeah, so I'm seeing that there is no any restrictions that says virtual function cannot be coroutine, so I just want to have a kind of confirmation.
If I'm not mistaken, yeah, it shouldn't be a problem.
Okay, cool. And the second one, so probably it's really stupid, but of course we know that for the plain function we cannot return any stack argument as a reference or a pointer, since that's direct reference or direct pointer. So, but for coroutine, if I have, for instance, some variable, I'm not sure whenever it's correct say to stack, but anyway, somewhere I declare local variable in the body, can I return maybe a reference or a pointer to that variable?
Yes, you can. One of the things that the compiler does is generate this special storage for the coroutine state. And that storage lives just like the scope of the execution of the body. So if you're yielding a value in mid-computation, those objects are still alive. And they will be destructed when the coroutine object is destroyed.
Okay, thank you.